Hello, everyone, and welcome to today's webinar on nanostructure transport characterization presented by Zurich Instruments. My name is Jorge, and I will be your host for today. I am based in our U.S. office in Cambridge, Massachusetts. Our U.S. office is conveniently located to support our customers based in North and South America. Today's webinar will be presented by Jelena, who is a product and applications manager based in Zurich, Switzerland. She has extensive knowledge on the topic of transport characterization and is an active member of the transport community, attending conferences and providing application support to both experienced researchers and those new to the field. Before we proceed, there's some important information that our audience should know. Today's session is being recorded, and the recording will be available to everyone at a later date. The audience's cameras and microphones have been disabled to conserve bandwidth to keep this a smooth experience for everyone. The chat feature has been disabled. Questions can be asked during the presentation using Zoom's Q&A feature. We will have a short break in the middle of the presentation to answer any clarification questions that the audience has before we proceed. There will be a final question and answer session at the end of the presentation, where we will try to answer as many questions as time allows. All questions that are unable to be addressed in today's session will be addressed at a later time, and the answers will be provided to our participants. Now, I'd like to share a little bit about Zurich Instruments for those of you in attendance that are new to our company. ZI's mission is to provide the best in-class dynamic signal instruments for advanced research and development labs. We achieve this by combining high-performance hardware with efficient workflow software to create instruments such as lock-in amplifiers, arbitrary waveform generators, quantum computing control systems, boxcar averagers, and impedance analyzers. Our great instruments would not be possible without our great team, composed of scientists and engineers from around the world. We don't just aim to provide the best in-class research instrument, we also provide premium customer care. We are fellow researchers and engineers that you can come to for help with lock-in and other instrumentation measurement techniques. We are here to help you get your application measured so that you can publish great work and advance science. Now that you know more about us, I will hand over the reins to Jelena so that she can speak today about nanostructure transport characterization. Jelena?
Thank you, Jorge. Thank you very much for this great introduction. Let's start with today's presentation. Just one thing that I'd like to clear out before we start is that I'll be using this pointer throughout the presentation to point to relevant parts of the slide so you can follow a little bit better. Okay, so today's talk will basically consist of three parts. So in the first part, we will give motivation as to why it's important to study nanostructures, as if the physics is not enough. And in the second part, we will talk about how we do transport measurements and what are the most important tools in order to do that. Then we will make a mid-webinar break with questions that you can ask. And in the last part, we will talk about the systems that we characterize and what do we get out of this characterization. Okay. So nanostructures are basic building blocks of today's modern computing and storage devices. In principle, the capacity and the speed with which the information is transported closely depends on the materials which we use to construct these devices. And the way to understand how they work and why it's best to use certain materials, we need to be able to characterize them. And for this, transport measurements are invaluable and give the best insight in how to do this. And in this process, we'll look at the transport of charge, spin, heat, and many other quasi-particle phenomena. And in this particular presentation, we will just focus on the charge transport. So let's see how this is done in practice. So in principle, when you start with a conductor, we want to look at the transport of charge carriers. And in order to do that, we first need to put at least two metal contacts on the side. And basically putting some DC bias on top, we apply voltage, we measure the current, and we can calculate the resistivity or the conductivity. And if you do it as a function of temperature, then we get a graph like this, which show, for example, a curve that's typical for metallic structures, or if we put a semiconductor between these two electrodes, we get these typical behavior where the resistivity or resistance diverges at low temperatures. And we know that this is basically happening because the current that we measure is proportional to the number of available states at the Fermi level. And we know this from the band structure of metals and semiconductors. We can easily calculate the density of states for these bulk materials. It goes as a square root of energy. For semiconductors, we see over here that we have we see the gap appearing. So all this is important to know, and we see this in the transport when we do these measurements. And now if we want to go to nanostructures, what we really need to do is to reduce their dimensions. And by doing that, we basically confine the electrons into these 2D sheets for 2D structures, 1D nanowires or wires for 1D, and for 0D, we have quantum dot type of structures. And what we note basically is that all these dimension reduction has fundamental impact on the density of states. You see completely different behavior, the constant density of states after certain energy in 2D materials. We see diverging number of states approaching certain energies, and we see only single available states for conduction, discrete states that are described by Dirac delta functions in say, zero-dimensional systems. So now if we further continue to reduce the dimensions of the systems such that they're much smaller than the characteristics wavelengths of the carriers, what actually happens is that the electronic wave functions forms standing waves and discrete energy levels. And what we really want to know is where these energy levels are, in order to be able to manipulate them further. And now what happens in these reduced dimensions, we have a set of we have a playground of states that we can play with and combine all these structures, including the bulk, into one single device, and make something useful once we're done with physics. And of course, what's important to note here is that in order to access these states, we have to be really careful because the energies are quite small, and anything that comes into the system, be it the heat or radiation, can smear and broaden the states, and we can basically lose the capability to observe them. And that's why all these systems need to be studied at low temperatures. Typically, you would not have this big cryostat, but any cryostat will do to go down to low enough temperatures which allow you to perform these studies. And cryostats not only cool down and make sure that these devices work at optimal temperatures, they also shield them from the noise, from different sorts of heating. And of course, they need to make sure that the noise also doesn't come from the instrumentation that's attached to the experiment. So one of the biggest problems that we can have in these experiments is basically the noise that's surrounding us. So how do we measure the noise? Well, basically, we can do this simply by using an oscilloscope. What we need to be able to measure is the noise spectral density as a function of frequency. And you see here a typical spectrum, which basically where noise increases as you go down to DC, goes as 1/f, and then flattens out in a white noise spectrum. And in principle, when we want to measure our device, we need to be able to navigate this space of different noise sources that and experiments typically has. And the instrument and the technique that's suitable for this is lock-in technique that's traditionally used in these types of experiments, not only because there's lots of noise, but our signal is very small as well. So let's see how lock-in amplifier works and what you should expect from a lock-in to provide. So in principle, lock-in should measure the amplitude of and the phase of the signal that we want to measure. The signal arrives into the lock-in inputs together with lots of noise, and lock-in needs to be able to distinguish between our signal by using the reference. So at the end, we can find out what is the amplitude and the phase with respect to reference. So how is this done in a little bit greater detail? It's done with a process called demodulation. So it's basically a mixture of mixing, or it consists of mixing and filtering. And the way you can see how this works is if you present your device that comes, your signal that comes into the device as a sine wave with a certain amplitude and phase. And of course, your reference signal also has a similar waveform. And what you need to do basically is to mix these two signals. And what it means is basically you need to multiply them. And by multiplying them, in and out of phase of the reference signal, so with 0 and 90-degree phase shift, you get two terms in each of these calculations. And basically, both terms consist of one that's proportional to the amplitude and has cosine of the phase. A second one as well, and also they have a time varying signal which with period of 2 omega, or two frequencies of the signal that we put in the system. So what we really want to do is we want to get rid of this part over here, and the way we do that is basically is by adding low pass filters after this signal, and at the end we get X and Y components of our measured signal, which contains both desired characteristics, so the amplitude and the phase. And after that, we can calculate them, and lock-in can give these as output. So these are really the two numbers that you should expect at least from a lock-in. So let's now see how the filtering goes. So the filters are low pass filters. They can be first or higher order filters. As you can see here, they are typically Butterworth type of filters, and their main characteristics are filter bandwidth and the time constant. So basically, they're inversely proportional to one another. So if you know one, you can easily calculate the other. And the very important is to sometimes think also in terms of bandwidth, because the bandwidth, the 3 dB point, is the point where the filter has emitted half of the signal power. And basically what it means, if we look at this graph that shows the signal as a function of time with different filter bandwidths applied to it. So in the case of 100 kilohertz filter bandwidth, we see lots of noise coming into the system. It goes down as we further reduce the filter bandwidth. And finally, at 1 hertz bandwidth, we see that we got rid of most of the noise, and we only are left with the intrinsic fluctuations of our system. So what's important to note here, right, that reducing the filter bandwidth really increases the time constant. You do get less noise, but you also need to do your measurement much more slower. So now with this next slide, what I would like especially graduate students to pay attention to is filters. They're very useful, but they can also be tricky, and they can be a source of error in the results that you read out from the lock-in. And that is because the filters need a certain time to settle. So in this graph, we see the step response of 4 filter orders from first to the 8th as a function of the time constant tau. we see that the first filter order settles pretty fast, and as we increase the order, the settling goes much slower. So if you're in the lab and you say, okay, I really have lots of noise, I need to reduce my filter bandwidth or increase my time constant, so let's say it needs to be 1 second by measuring at low frequencies, and then you say, well, okay, I can then now get the data from my lock-in after one second. And what this really means is that you're sampling your data at this particular point, and the higher the filter order that you choose, the bigger the error that you actually make in reading out the results from the lock-in in this particular case. So this is something that you should have in mind. You can look up our user manuals and see a little bit more about this. And all this that I said so far is true for any of the lock-ins that you have in your labs, the ones that you've been working with as I have, and all these instruments should in principle be able to clearly give you these two numbers, which are the result that has less noise, so you have higher signal to noise ratio. So now let's see how lock-in amplifiers from Zurich Instruments are made and what you can expect from them. Well, first of all our lock-ins have FPGA board inside. This FPGA board allowed us to make a variety of lock-ins. Not only that, but in principle we have lock-ins that span from 500 kilohertz to 600 megahertz operational range, and this is because we have basically different sampling rates of the ADCs of these lock-ins. We have different operational range, but we also have different filter bandwidths that we can use in these lock-ins. So in principle, depending on what type of experiments you have, you can choose which lock-in you want to have for your measurements. And this is not all. The FPGA board also allowed us to have numerous tools built in our lock-ins. So in addition to scope, sweeper, plotter, we also have spectrum, numerical tab, of course, that you expect from a lock-in, but also a number of additional options that you can add anytime during your experimental work. And all these tools and options work together underneath a Lab 1 user interface that we built such that you can do the best experiments in your lab. So let's see a little bit more about the user interface. Here's an example. It's built in the web browser. You can run it in any web browser of your choice. And I show here the two most important tools that you always have available while doing your experiment. So first one is the plotter. So the plotter basically plots your data in real time. You can plot also data from auxiliary outputs. You can plot the magnetic field that you sweep or something that's proportional to temperature. And at any point when you do different filter settings, you can calculate the mean and standard deviation of your signal, and you can really see the dynamic of your signal changing during any of the sweeps and decide what are the best conditions for doing your experiment. And second tool that I find extremely useful, because it's always there in every instrument for every input that we have, and that's the oscilloscope, which you can use to characterize your system when it comes to noise measurement and different debuggings. So it runs both in time and frequency domain, and this way you can take all these spectra, you can change the sampling rate of the scope, save the data, and use this as a reference for showing how good your instruments are. And I also wanted to point out here that in addition to the oscilloscope, you can use a digitizer option, which gives you full ADC resolution, and you can do even better noise measurements with this option. So now talking about the experiments and how the noise is important to handle, the instruments that you have in your transport measurements basically also need to be low noise. And they need to be, because they're always adding the noise together with your experiment. So this is here we show the input noise characteristics of one of our lock-ins, and it's important to look at these characteristics, especially if you know that the signal that you're trying to measure is on the order of nanovolts or less. So you need to devise different strategies how you're going to measure it. And another important characteristic of the noise with which locking or instrument can contribute negatively to your experiment is the noise dissipated from the inputs. It can be at such frequencies that directly increases the electronic temperature. So let's say your thermometer shows something like 10 millikelvin, but your electrons are at 50 millikelvin, and you see that something doesn't add up in the experiment. So this is something that you need to be aware of. And finally, you need to be aware of the dynamic reserve capabilities of your instrument. So you want to measure really small signal compared to with the nearby disturbance. And in order to do that, the dynamic reserve of your instrument has to be big enough such that the measurements can be done accurately as well. And you can see this also in the spectrum tool by doing the FFT of the demodulated data. So in this particular case, when you have these bunch of these 50 hertz peaks, you either go and clean up your setup or change. If you can't do anything about the setup, then you have to change the filter settings or notch these peaks. Okay, so all these tools that you have available actually in Zurich Instruments lock-ins are invaluable for doing the full sample characterization. And if what I said so far is not enough noise-wise, you can always also run the lock-ins on a battery. Okay, so before we're now going to make a break. We're going to have a mid-webinar pause. We're going to have your questions. I think Jorge can take over now.
Great, thank you, Jelena.
Thanks.
All right, perfect. So we'll go ahead and answer some of the audience's questions. The first question they have for you is, you mentioned that the instruments fits well with cold temperature experiments. Is it also possible to perform room temperature measurements for transport?
Yes, of course. All these transport measurements are possible to perform at any temperature, of course. Yes, so this is possible.
Perfect. And then the follow-up question to that is, do you have an analog interface which allows you to talk to like a fridge or some kind of communication between instruments?
I don't fully understand the question.
I'll help you out with that. So we actually have a DIO port in the back of the instrument that you could use to communicate between instruments. And if you need some kind of trigger pulse or things of that nature, our instruments have output triggers, input triggers, and you can have auxiliary outputs that respond to some signal to feed a voltage to another instrument.
In addition, okay, if that is the nature of the question, basically you also have TTL inputs and outputs. You can also synchronize the clocks of different instrumentation. Yeah, so these are all available.
Oh, perfect. Thank you, Jelena. And then someone's asking about the filter settings that you discussed. They mentioned that it's something that's very important. What kind of advice can you give for optimizing which filter order you pick?
Okay, so in principle, you have to have a bit of a trade-off between the speed of your measurement and the quality. So I would let's say go from one end of the spectrum. Let's say I would first do some rough estimate, open the filter, slowly start closing it, reducing the bandwidth. Maybe I would add one more filter order, and basically see when you stop seeing any significant improvement by adding the filter, and then you basically see how long it takes for the filters to settle and so on. So it's a little bit of optimization process.
Oh, I think you're having some audio issues, Jelena.
Have audio issues?
Oh, there you go. Now it just cut out for a little bit.
Okay. So I answered this question. I think I hope whoever asked it heard me, and we can continue also after the webinar email if you have more questions.
Excellent. And then another question from the audience is, you mentioned that you can run the instrument off of battery to reduce the noise. Will the computer connection to the instrument introduce any noise to the measurement?
Yes, in principle, computers can also contribute to doing this. However, you can store at some of our lock-ins. You can store you can start running the experiment and store the data directly on the lock-in. So you don't really have to have it connected constantly via computer. But let's say USB connections are quite interfering in this respect, but we also have LAN connection to all our lock-ins, so you can also try that.
Perfect. And then we have another question about interfacing our instruments with some kind of controller like Python or MATLAB or LabVIEW. Do we provide the drivers?
Absolutely, we provide all these drivers, and we have extensive library of examples. We're happy to talk to you to hear what you want to do if we don't have something that you want to measure. So this is a standard part of our offering.
Perfect.
Great.
And someone was asking if you could just speak a little bit more about dynamic reserve, just so that they can understand it a little bit better.
To speak about it a little bit more. Okay. Well, in principle, you sometimes have maybe you want to measure a couple of signals at the same time. You don't necessarily need to have a disturbance that you can get rid of, but in principle, it's important to be able to measure each of these signals with the accuracy that you want, or that's spec'd. Together with this nearby signal that also contributes to the noise with its own power. So basically, lock-ins are able with their filtering capabilities to also withstand that. I think we can move this, and I can get back.
Get back to the. All right. Yeah, then I'll hand it back over to you.
All right. Okay. Well, keep on asking questions. I'm sure we can answer them also after the webinar. Don't stop with that, and also tell us what type of experiments you do while you're at it, if you have the time. Okay. So moving next, we want to see how the transport measurements relate to the lock-in output, and how can we measure all these components of transport. When we go back again to our conductor, we attach the leads, and basically what we see in this particular configuration that we can apply some AC excitation, apply some digital or analog bias to this structure, and as a consequence over here measure the AC and DC current. And the way this basically looks like in case of ohmic contacts to your conductor is you have maybe linear IV characteristics, and this is something that you can measure with our lock-ins in DC. But what happens in AC basically is that at any point of the applied DC bias, the lock-in superimposes small AC excitation to this curve. And as a consequence, a current is being, AC current is being generated and measured, and this is exactly what lock-in is measuring. So in the case of linear characteristics, as a function of DC bias, your lock-in will show a flat conductance or flat current versus voltage characteristic. Similarly, now if you have system with let's say non-ohmic contacts with barrier between your contact and the conductor, you sometimes want to study this. And sometimes you want to get rid of the contacts which are nonlinear. So in that case, what you will get is basically these nonlinear characteristics, which again, the lock-in will take derivative of it, and you will know what the differential conductance of this conductor looks like. And now we can also, getting rid of the contact resistance, we go over to 4 terminal measurements. We put 2 leads with distance L on this conductor. We can measure the differential voltage, and based on our current and voltage measurements, we can calculate the differential resistance of this particular conductor. And this is basically a standard set of outputs that you can and measurements that you can expect from this lock-in. And how is this possible? Well, in the basic form or basic type of lock-in that we have, also like conventional lock-ins has only a single frequency to measure, and you have to choose between voltage and the current that you want to measure at a time. But if you add the multi-demodulator option, this gives you a great opportunity to measure at 4 different frequencies, because you have 4 dual phase demodulators. You can measure current and voltage at the same time. You can measure higher harmonics, and this really gives a lot of flexibility and possibility in this one box. And just to show you one example how that looks like, if you want to measure in DC, basically you need to put 0 as a frequency for your lock-in, so that the modulator over here will be measuring over here voltage, and in this demodulator it will measure current. So you have your DC IV characteristics, and then you can set some AC frequency for oscillator number 2, and that allows you to measure the AC conductance and also second order conductance with the lock-in. And also within the lock-in user interface, you can choose what type of DC biases you're going to apply, whether you're going to sweep them, and so on. So what are the various applications, or what are the different characterizations that you can do with these systems? Well, first of all, there's many of them. It's impossible even to number them. However, what we can give you a couple of examples here is basically, in addition to this complete nanostructure characterization, you can do Hall effect measurements where you can calculate or measure carrier density and mobility. You can do full noise characterization of your devices. You can measure something like spin Hall effect where you need higher harmonics. You can measure also thermal conductivity. One examples are 3 omega measurements. And of course, if you make hybrid structures, you can characterize each component of this structure. And by hybrid, I mean if you connect, let's say, superconductor with a metal or a semiconductor, and all these hybrid structures have interesting interface characteristics where you can basically do tunneling spectroscopy, you can do spin polarization measurements, and so on. So there's plenty of things you can do. And as someone already noted, you don't need to do all these just at low temperatures. These are also benchtop experiments done at any temperature that you need, where your physics is. Okay, so let's go now to carrier density and mobility measurements by using the Hall effect. Actually, this is an example where, in principle, you need 2 lock-in amplifiers, no matter which ones they are. And for the Hall effect measurements, it's best to shape your sample into this whole bar geometry. So in this longitudinal direction here, you have the current flow, and in the perpendicular, you would expect to see some carriers being deflected because there is perpendicular magnetic field applied, and due to Lorentz force, we have electrons or whoever is conducting also spins will basically go to the sides, be deflected to the sides of the sample. And there are a couple of things that and approaches that you can have for these types of experiments. So first of all, you need to generate some sort of constant current your sample. And very common way to do this is by putting the so-called current limiting resistor, which will be such that its resistance is higher than all the resistances combined in your sample. And basically, you need to make sure that throughout the measurement, and when you sweep the field, these conditions are met. And if you're not sure, it's actually very important to be able to measure the current. And this is something that you can do with this second lock-in that's on the side. So what you do over here, the lock-in, let's say number 1, will measure the whole voltage, VXY, and the second lock-in over here will measure the longitudinal VXX voltage. And by doing such measurements, when you sweep the field, you have in classical case you have linear whole voltage, and the VXX in principle should not be field dependent. And using all these measurements, you can then calculate the carrier density. So you will see that in semiconductors, you can infer what the doping is, and so on. And in addition to these measurements, you can also infer what the mobility is. That tells you what are the scattering mechanisms, and how much scattering do the carriers experience during the transport. So this is something that's really standard, and again to emphasize, this is not just low temperature. You can do this if you have a magnet that you can apply on top of your sample. You can do all these measurements irrespective of the temperature. So this was the case of the classical Hall effect, very useful. Throughout the studies of the Hall effect, and especially when it comes to 2D materials, what was discovered basically, and what's also one typical measurement is the quantum Hall effect measurement, and this is exactly the showcase of the quantized conductance or the resistance that we see in this system. If you remember from the density of states that we already showed, so we see that each time the electrons are on certain energy level, the resistance stayed the same, Hall resistance stayed the same, and of course the electrons in the longitudinal directions don't experience any scattering, so the transport is without any resistance. And this can be also seen in a little bit more detail in our application note shown here. So these are the actual measurements, quantum Hall effect measurements. You can see that one of the challenges of this measurement is basically these constant Shubnikov de Haas oscillations, which carry a lot of important information. For example, here there is a signature of spin splitting, and you really want to know at each level of the signal from bottom to top. You want to have the high resolution of your measurement, and this is one of the challenges that let's say lock-ins and especially in this particular case our lock-in managed to overcome, and to be able to do these measurements with high resolution, such that you can discover new effects in these systems. And now the next very interesting system that I really like and I worked on is graphene, and it's not just graphene, but there's a whole host of 2-dimensional systems that can subscribe here. So these systems are interesting because of their curious band structure. So graphene is an atomic layer of graphite. So one atom thick layer of graphite. Here it's kind of plotted in a whole bar structure. There is a silicon dioxide layer underneath and the doped silicon layer, which basically will serve as a backgate. So graphene has this linear dispersion relation which is quite unique, and it shows these characteristics even at room temperature. So what we do when we apply the backgate voltage in graphene, we basically move the Fermi level from the electron to the hole states and back, so we can basically tune the conduction in this system over on this side from electrons over here to holes, and we see that the conductivity has this minimum value that corresponds to the Dirac point over here, and all these is basically possible to measure using typical lock-in technique, where you need to apply substantial, not anymore, but it used to be important to apply substantial backgate voltage to see these effects, but they persist up to room temperature. And now we're going to switch gears a little bit. We're going to go into the quantum dot systems, and these systems are very important for quantum computing devices, because Loss and DiVincenzo are one of the proposers of 2D electron gas carved into two quantum dots as a candidate for spin qubit. So as this is really an important proposal, it's important to understand what are the characteristics of electrons and spins in these quantum dot structures, and also to understand that these structures can be made in various different systems, for example, carbon nanotubes, graphene quantum dots, and many other. And for the sake of today's showing how this is done, we will look into the quantum dots made in carbon nanotubes. So let's see how this is done. So here is an example of or the plot of a carbon nanotube that you can see over here. So in order to make quantum dots in carbon nanotube, you really need to contact it with two metallic leads, and the coupling between these leads and a carbon nanotube has to be weak, such that the electrons that are trapped inside and their wave function cannot escape this potential well, and we have energy levels formed within the carbon nanotube. They are fourfold degenerate. We won't go into why this is happening, but in order to observe the transports in carbon nanotube, what we need to do, we need to move these energy levels by using the backgate voltage, and we can also sweep the source and drain electrodes. So this is source and this is drain, by using a DC and AC excitation, so typical lock-in technique, and look into this transport through this quantum dot. So what we see over here is basically the plot of what we should expect. So over here is the backgate voltage, and each time you move the backgate voltage, you get one of these levels closer to the source lead. And when they basically align, you can expect an electron to jump into the dot and start conducting. However, this doesn't come for free. You need to pay the price of charging energy, because these walls don't let the electrons come out, but they also don't let them come in. And then you see these additional steps or peaks in the conductance. Each time we add one electron into these energy levels, next electron need to be with spin. Spin up can be over here, next two ones need to be spin down, and so on. So we have, as also function of a source drain bias, we see these really nice Coulomb diamonds, which we can also see in the lock-in measurements, right? So this will be the typical, or well, maybe not so typical, but still one type of the conductance as a function of backgate voltage. And if we then sweep the source drain bias, we see these Coulomb diamonds. And these measurements are typically being done at low frequencies, which for this very detailed plot means that it takes a lot of time. And if you think about these quantum dots or double quantum dots as candidates for spin qubits, and you want to have many of them. So in order to understand where are the states of the dots, you really can't afford to do these hour-long measurements using the conventional lock-in technique. So the way to actually speed up these measurements in quantum dot is to attach something else to the leads of the dots. So over here we have double quantum dot system. So instead of simply attaching a DC bias and some low frequency AC excitation, what we need to do basically is to attach a resonance circuit, and such that together with quantum dot has a 50 ohm impedance. So when it's connected to the RF source, which allows you to do faster measurements, you can then have transmission of this signal without any reflection. This part of the circuit over here is resonant. You can see over here how the resonance peak changes as a function of frequency. This is the phase. And the essence of these measurements is basically that you set your lock-in somewhere where it's very sensitive to any changes of this circuitry here, and this will happen each time the electrons come in and out of the dot. So the capacitance changes in this case, and so in principle, when you position your lock-in over here somewhere, you will be very sensitive to very small changes to basically resonance frequency, and you will see the change in your signal due to the any population or depopulation of the dot. And this is something it's possible to do. These experiments are done, as you can see, at this and even higher frequency. And with Zurich Instruments lock-ins, MFLI is the lock-in that really enabled our users to do these measurements in a matter of seconds instead of hours. So they get these beautiful Coulomb diamonds fast, and they can move on and doing their measurements towards the spin or any other qubit type of computation. I think this is basically the end of my talk. What I'd like you to conclude with, I hope you've been able to follow what we talked about. Basically, is that transport measurements are a crucial probe to find out about the characteristics of nanostructure devices, to see what their physics are and how you can use it to your advantage to build even more powerful devices. We've seen that Zurich Instruments lock-ins have many more capabilities. Actually, they can provide you with full suite of measurement tools, such that you are confident and can do good measurements. And furthermore, you can do with different types of lock-ins from Zurich Instruments, you can do extremely fast characterization of these devices and measure one single point with tenths of nanosecond time. So that will be all from me. Thanks very much for this. Let's now go to the Q&A session. We still have the time. So Jorge, I hand it over to you.
Excellent. Thank you, Jelena. Thank you for the great talk. So the first question, something you just kind of finished talking about, is are there any other ways to speed up the measurement in the lock-in?
Yes, that's a little bit general question, but in principle, yes. If you just look at the conventional lock-in technique, of course you can speed up the measurements. So, for example, I mentioned earlier that this 2 omega component is something that's always in your way. So especially if you do measurements at low frequencies, your 2 omega component, let's say, will be very close. So you have very little space or very little filter space to play with. So what you can do, you can use the sync filter, which is a notch filter, and basically notch this 2 omega component and go a little bit wider with your filter bandwidth.
Okay, thank you. A clarification question from one of the audience members is in the Hall effect measurement you showed, why do you connect the drain to another lock-in than the one generating the source?
Okay, I would have to take a look at that. Let's see.
One moment, she brings up that slide.
My Hall effect measurements. Aha, I think I know where this question. So where it is. Okay. I think this is the slide you're talking about.
Why am I?
Is this the, well, I don't know if this is the one, the Hall effect measurement. So let's see what's next here. So that's the only Hall effect measurement. I don't fully understand the question. So let's
I'll clarify it. So they're asking why do you need two lock-ins?
Sorry?
Well, why do you need two lock-ins for this measurement? It can't be done with one?
No, well, you can do with one, but you can't do the measurements at the same time. So you would have to switch between. I mean, if you really want to do a careful low signal measurements, then you should do with two lock-ins.
Perfect.
And they have to be differential in a way, yes. So that's also the reason.
Excellent. Thanks. The next question from the audience is, how do you avoid heating during the transport measurement?
So the heating you avoid by doing additional filtering. So you need to be able to first of all check what is the electronic temperature, and you can do this. There are various ways you can do this, and if this is not enough, you need to well, do better with filtering.
Perfect, thanks. Follow-up question is, how do you reduce the 50 or 60 hertz line noise besides using the instrument on a power line? I'm sorry, on a battery supply.
Well, basically, you can have devices that can break the ground loops, and so this is something that can be done by looking where the noise is coming from. I mean, there are various different ways you can do this.
Excellent. And another question is, can you source a current signal instead of a voltage?
Can you source a current signal instead of voltage? Yes, you can.
Okay, and how would they do that?
Well, here is the example. Basically, having this exactly on this slide, you have a current limiting resistor. So basically, it will have the resistance larger. It will be in series and larger than anything else that you have in the circuit, and in principle, you then source the current. There are also other ways. You can have additional devices attached to the lock-in that can transform voltage into current and so on. And you can also have a current source.
Excellent. And then during your talk, you mentioned additional options that are available for certain experiment tool sets. Is that something that you have to buy initially with the instrument, or can you add them on later?
No, you don't have to buy them initially. You can add them anytime later.
Perfect. So if you think you might need something, but you don't need to start with it, you can just buy it later. That's
yes. Perfect.
Okay. And you mentioned that we have a sweeper that can basically sweep the spectrum of your sample. Does it automatically adjust the bandwidth for the filter settings for the sample to settle as it's sweeping?
Yes, we have several. We have several options, and it's quite exhausting. The number of options we have to do that, and it's very important to have it. The auto bandwidth is always there by default. You can basically, based on the number of points and the frequency distance that you want to run your sweeper with, and also if it's linear or log, the lock-in will automatically adjust the filters for each of these points, and you can do this in the beginning really fast, but later on you can basically have, let's say, fixed fixed filter bandwidth if you want to be even more, let's say, accurate in your measurements and so on. So all these options are available.
Perfect, perfect. So another question is, so it's claimed that analog lock-ins have lower noise than digital FPGA-based lock-ins. What do you have to say about that?
Well, it was certainly true before, definitely when there was a transition between really fantastic analog lock-ins from Princeton Applied Research, and then naturally the technology went digital, and experiments have really suffered a lot from the noise, digital noise coming from these lock-ins. In the meantime, the ADCs and the whole technology has improved, and this is no longer the case. If you let's say take a look at the study that we did with our lock-ins, you will see that in one of the technical notes that I've showed, you will see that digital technology is now way better than in the 80s or 90s.
Perfect. So we'll go ahead and include a link to that paper that you mentioned when we upload these questions and answers. Another question is, can we interface our instrument to, say, a LAN connection to have multiple users access the instrument from different computers?
Yes, this can be done.
Perfect, perfect. And then another question is, how many harmonics can be measured simultaneously with our instruments?
Well, that's actually a very important question for many of the users that save them from getting a lot of lock-ins on a single setup. So in MFLI, the lock-in that I showed the most, so this is the 500 kilohertz lock-in. Move my mouse. So, okay, I will just say it because I can't find the slide. So for MFLI, it's basically, you can measure four harmonics in total, or you can measure fundamental and 3 higher harmonics. In HF2LI, it's 6 in total, and UHF-LI, 600 megahertz lock-in, it's 8 harmonics.
Excellent. Perfect. And then I guess the last question is, someone mentioned that they really enjoyed this seminar, and if we're going to do more. And yes, we are, and we'll have a slide later with a link to where you can go to see our upcoming webinars.
Yeah, we'll definitely. Can I just say one thing? We'll definitely do more. And if you have ideas, or I mean, we do have our own ideas, but if you also want to contribute, and also if you want to be part of one of our webinars, we will be happy to hear from you and plan something for the future. That's all
Excellent.
I wanted to say.
That is a great point. You know, being unable to present research at conferences due to COVID, if you guys are interested in doing a joint seminar where we kind of talk about the instrumentation and you present your work, we'd be definitely interested to hear from you.
So let me switch.
Oh, perfect.
Let me just switch. So these are the next ones. And the upcoming webinars, is this something that we mentioned?
Correct. So, you know, of course, we want to stay engaged with our users and the research community. So stay tuned to our upcoming webinars. You can see more of our complete list on our website, which we have here. And then finally, thank you very much for attending today's webinar on nanostructure transport characterization. I would like to thank Jelena and the rest of our team who helped put this presentation together. If you didn't have a chance to get your question answered during the presentation, or you have a question that comes up later, reach out to us. We look forward to helping you get your application measured. Thank you. And just so you're aware, we anticipate having this recording out to everyone in 1 to 2 weeks. Thank you so much for your attention.
Thank you. Bye.
Bye, everyone.